Unit 9 or Chapter 9 is Chemical Bonding Part 1, Basic Concepts. Bonds give compounds stability and a set of properties that are different from the elements used to form those compounds. An ionic compound is the electrostatic force between a cation and an anion, and a covalent bond is the intramolecular forces between two nonmetals. So they share electrons either equally or unequally. Lewis dot symbols. So Gilbert Lewis was an American chemist who showed how the periodic table and electron configurations give us rationales behind the bonding. Atoms combine in order to achieve a more stable electron configuration. Maximum stability results when an atom is isoelectronic with a noble gas. When atoms bond, their outer regions interact. So bonding is really about the valence electrons. So we need to keep track of valence electrons. And for any bond, the number cannot change. So if you start with 5 valence electrons total, you have to end with 5. Lewis dot symbols then are named for Gilbert Lewis and consist of the symbol of the element and 1 dot for each valence electron. So if you remember that the last digit in the group number is how many valence electrons it has, except for helium, because helium only has 2 electrons. That's a quick way of drawing Lewis structures. So an ionic bond, you have cations that are typically from group 1 or group 2. The anions are typically from group 8A or oxygen. So an ionic bond, you have the electrostatic force that holds the ions together. The actual formation of this bond actually occurs in several steps. We have to take the metal from the solid state that it's found in at room temperature and change it to the gas phase. The ionization of the metals that has to occur, the metal has to lose the electron. Dissociation, if it's a diatomic, has to happen, so F2 becomes 2 fluorine atoms. And then the anion has to have the electron added to it, or electron affinity. Then we have to take our gaseous cation and our gaseous anion and put them together. So it doesn't happen in one step. It happens in a series of steps. However, it doesn't have to be rigid 1, 2, 3, 4, 5. It's just these 5 things have to happen at some point. Alright, so for example, for Lewis dot symbols, let's represent barium hydride. So we have barium. Barium is in group 2, so it has 2 valence electrons. Hydride refers to our element hydrogen, which only has 1 valence electron. Now, barium, being the metal, is going to give hydrogen its valence electron. Now, hydrogen only wants 2 electrons to be isoelectronic with helium. So this hydrogen will not accept barium's other valence electron. So we actually need another hydrogen atom. And now our barium can give away its second valence electron. So if we were to write a reaction, we have barium reacting with 2 hydrogens and that's going to form Ba plus 2 plus 2 hydrogens with 2 valence electrons. This could be written simply as BaH2 then. Lattice energy of ionic compounds. So we can predict which atoms or which elements will make ionic compounds by using ionization and electron affinity values. But how do we know if the compound formed is stable? We use the lattice energy. So the overall stability depends on the interactions of all the ions, not just one cation and one anion, because they form these complex lattices. So instead of just having sodium and chlorine, you're going to have another sodium, another chlorine, which is on top of a sodium and a chlorine and a sodium and a chlorine. You have this 3D structure, so it's not really one atom with one atom. So the lattice energy is the quantitative measure of the ability of, or the stability of any ionic compound. The Born-Haber cycle is determining the lattice, is what we use to determine lattice energy. So lattice energy cannot be measured directly. We can calculate it if we know the structure and the composition. So Coulomb's law says that the potential energy, or E, between two ions is directly proportional to the products of their charges. So if you're doing lithium chloride, it'd be +1 times -1, divided by the distance between them, so divided by r, their radius. Since the cation is positive and the anion is negative, then E is going to be a negative quantity. So the process of forming the ionic compounds is very exothermic, which means the reverse must be endothermic. So lattice energy is always endothermic. Lattice energy, the larger the charge, +1 times -1 versus +2 times -2, the larger the charge, the larger the lattice energy. The smaller the atom, the larger the lattice energy. The larger the lattice energy can lead into the different properties. So the Born-Haber cycle relates lattice energies to ionic compounds, to the ionization energies, the electron affinities, and other atomic or molecular properties. So it's really based on Hess's law from chapter 6. So ionic compounds are formed, again, by a series of steps. It doesn't necessarily have to be in this order, but you first need to sublime the metal. So you have to take it from the solid state to the gas state. You need to dissociate your halogen if needed. So F2 going to just F. And you can see the different values there. Then we need to make them ions. So the lithium here is being ionized, and the fluorine has electron affinity associated with it. And again, you see the values. Now when we put these two things together, it's going to form, or that's going to be our lattice energy. Now it's a negative lattice energy, not just lattice energy. So the overall, if we were to add up the individual steps, the overall process is negative. So the overall process is exothermic. The greater the lattice energy, the more stable the ionic compound. So again, we like to have those charges to be large and the size of the atoms to be small. So the lattice energy is always positive because based on Coulomb's law, it's an endothermic process. But the overall energy change is exothermic, or negative. The larger the lattice energy, the more stable the solid, the more tightly held the ions. So when we say that the lattice energy is a large value, we're saying that those ions are really attracted to each other. And if they're really attracted to each other, then that can describe some of the properties that we notice, like melting points. So the more larger the lattice energy, the more stable the solid, the more tightly held the ions. So the more energy it's going to take to melt, so the higher the melting point. And you can see in this chart how you go from having +1 and -1 to +2 -1 to +2 -2, and the melting points would really start to jump up there.